Okay, so we are in chapter 3, and we're actually going to finish up chapter 3 today with section 3.3, which is Kramer's rule or Kramer's rule. You have learned in chapter 3 about determinants. In section 3.1, you learned how to do cofactor expansion for determinants. Yeah, that's right. And in section 3.2, you learn properties of determinants. And we understand that to do cofactor expansion, particularly for larger matrices that are dense, with a lot of non-zero entries, it would take a very long time to compute determinants using cofactor expansion. But in section 3.2, using properties of determinants, we can compute determinants much, much, much more quickly. Okay, and now that we know that, we can yet find another way to solve a system of equations using determinants. And this is known as Kramer's rule. Now they make a little comment right in the beginning. It's needed in a variety of theoretical calculations, Kramer's rule, and it can be used to study how the solution of a system of equations is affected by the changes of the entries in the constant vector on the right. And you'll get an intuitive feel for this when we do the Kramer's rule. The formula, though, is inefficient for hand calculations, except for 2x2 or perhaps 3x3 matrices. And that's because if you have, for instance, a system where you have 4x4 matrices, it could just, well, particularly cofactor expansion would take a fair amount of time. So, okay, let's see what's going on here with this Kramer's rule. Let's see how this works. So first of all, a bit of notation here. Okay, one moment. Okay, so you have a matrix A, and if you replace the column in the matrix A, the ith column in the matrix A by the vector B, you would get the matrix A sub I of vector B. Basically, the matrix A, it's the matrix A with its columns A1, A2 up to AN, except you replace the ith column with the vector B. Now, if we define that matrix that way, then it turns out Kramer's rule is given here. So of course, the matrix A has to be invertible. And if a matrix A is not invertible, then its determinant is going to equal 0. Okay, so and you don't want the determinant of your matrix equal to 0, because you see there in the x sub I formula, you solve for variables x1, x2, x3, x4, whatever. The x sub I formula has the determinant of A in the denominator. So determinant of A cannot be equal to 0, and therefore the matrix A has to be invertible. So for any invertible, let A be any invertible matrix, any square invertible matrix. This is Kramer's rule. Then let the vector B be a unique solution. Okay, well, no, for any vector B, the unique solution X has entries given by what you see there in the formula, what you see right here. Let me take that off. Right there. Okay. So very interesting theorem. And I think it would be a good idea for us to see how it's proven. So let's look at the proof of this. So I'll go to the next page here. And all right, what we want to do is we want to denote the columns of the matrix A by those column vectors A1, A2 up to AN, and the columns of the identity matrix by the unit vectors E1, E2 up to EN. That makes sense. That makes sense because we know that E1, like for instance, let me just go to the blackboard here. So we know that if you have the 3x3 identity matrix, looks like that, and here are the column vectors, E1, E2, and E3. So you can represent the matrix I3 in briefer notation this way. Okay, and so that's what they're doing. And by the way, if you had I sub 3 of the vector x, well, let me do this. Hold on. If you had, got to be a little careful here. To be honest, we don't want to use the 3 here. Okay, we don't want to have that there, even though I know you've seen it in your, because now putting a number there has meaning. Like if I go I sub 2 of x, this means keep column 1, keep column 3, but replace the second column of that matrix I by the vector x. Okay, are there any questions on this kind of notation here? Yeah, Mikhail? Mm-hmm. Well, the notation back in the book, they defined the matrix A. Well, it's matrix A sub I vector B. That would be equal to A1, the matrix whose columns are A1, A2, vector B. All the column vectors of the matrix A are there, except in the ith column, you replace the ith column of the matrix A with vector B. See? So it makes sense then that, right, it's defined in the book. So it makes sense that I sub 2 of x would be that vector, would be that matrix there with those 3 columns. Okay, all right, let's go back to the book. Hold on. Okay, you're welcome. You're welcome. Okay, so what we're doing here, just kind of highlight everything here. Well, no, I won't do that. Try to do it piece by piece. So if you take the matrix A times the I sub I x matrix, I sub I of x matrix, that's just A times the second matrix you see there. But where the columns are E1, E2, and then the ith column is replaced by x, you know. But you learned in terms of matrix multiplication then that you could represent the matrix product. You could represent this matrix product this way with a matrix with those columns, right? That's the matrix multiplication. You know, and well, if you have, for instance, if you have A times E1, that equals A1. A times E1 equals A1. Now, let's see if we can justify that with a little example here. Okay, so if A equals, 1, 2, 3, 4, and E1 would be equal to 1, 0, then, and by the way, I'll call first column A1, second column A2. Then if I take A times E1, I can do that because I had a 2 by 2 times a 2 by 1. And so using the row column rule that you learned when you learned matrix multiplication, you're going to get 1, 3, which is A1. So this means that A times E1 equals A1. And similarly, the matrix A times E2 would equal A2. Are there any questions on that? All right, well, let's go back to the proof then. We just want to we want to understand what's going on here, what they mean. So, okay, now we're back to here, and then what they do is say, well, this entire this entire matrix equals, hold on, I don't want that. Yeah, it equals the matrix A sub IB. So A times the matrix identity I sub IX equals the matrix A sub IB. And what they do is they take determinants of both sides. Okay, they take determinants of both sides. Okay, so you have the determinant of A equals the determinant of I sub IX equals determinant of A sub IB. But the second determinant on the left here, the determinant of I sub IX, is simply equal to XI. Hold on. Okay, now to sort of see that, whoops, hold on, what I do? Hold on, let me get it back here. All right. If you had, hold on here. So if you had I sub 3 of X, hold on. I sub 3 of X, that would be E1, E2, and X. And if we wrote that out, okay. So is this matrix here in triangular form? It is. Is it upper triangular or lower triangular form? Not that it matters, but that's right, Belen, upper triangular, because below the diagonal is the triangle of zeros, and above the diagonal, well, you have you have the x1 and the x2 here, so those can be non-zero, so upper triangular. Now, how do you find the determinant of a triangular matrix? Is it easy to find the determinant of a triangular matrix? It is. What is that determinant equal to? That's right, Mikhail. It's the product of the diagonal entries. So you get 1 times x3, and that equals x3. So I should add something here. Hold on. I should put in, I'm finding the determinant, right? Determinant equals determinant equals determinant. Okay, and there you go. So now that makes more sense in the proof of Cramer's rule, what they're doing there, what they're talking about. Okay, so if we go back to the, well, the equal would apply without the determinant, but up to this point here, up to that point, 1 times x3. Yeah. All right. So now, okay, so now, hold on here, I'm just trying to unhighlight what things I don't need. Yeah. So the second determinant on the left is simply x sub I. Therefore, the product, and I guess they use the fact that if you have, let me see here, take this off. If you have the determinant of A times B, that's just the determinant of A. Hold on, I like to make things look nice. If you have the determinant of A times B, that's just the determinant of A times the determinant of B. So that's another property of determinants. Okay, that actually is theorem 6 from page, theorem 6 from section 3.2. Okay, and while we're at it, I'll just mention theorem 5 from section 3.2. Theorem 5 says the determinant of A transpose is equal to the determinant. Okay, determinant of A transpose equals the determinant of A. That's another property. So given that now, I think we're basically good to go here, because now that we have this result, hold on, let me just unhighlight what I don't want here. Hold on. Now that we have this result, xi would equal the determinant of A sub IB over determinant of A. We can divide both sides of that equation by the determinant of A. Okay, so are there any questions? All right, well, let's take a look at this Cramer's rule. So here it is. And let's apply it to a problem here. Let's apply it to a problem. Let's look at example 1 from the book here. Hold on. Okay, use Cramer's rule to solve the system. So you see how you have the matrix A of coefficients of x1 and x2. The matrix A sub 1b and A sub 2 would be. Are we okay with those, with that? All right, Marcella's good. Mikhail's good, all right. Well, you know, we're just going to use Cramer's rule right here. And we get our answers. So the solution to that system of equations is x1 equals 20 and x2 equals 27. So that's solving a system of equations. Now, the book also, okay, let me just go down here. So they do another example, example 2, where they have some variables. The book also talks about finding another formula for A inverse. Okay, so you can actually use Cramer's rule to get a formula for finding the inverse. And the formula is right here. Okay, this formula, well, the A inverse is 1 over the determinant of A times the matrix of the cofactors for like cofactor expansion. And the right side of this formula 4 is called the adjugate or classical adjoint. And the book talks about that. And that's fine. It's another formula for finding the inverse. However, there are numerical notes that say that the approach that you learned in section 6.2, I mean, there's the formula there, but and that would work, right? But this theorem 8 is right here. Hold on. There's theorem 8, where the inverse is 1 over the determinant of A times the adjugate of the matrix A. But it takes quite a while. You can see in example 3, it takes quite a while to construct an adjugate because you have to come up with all the cofactors. It can take time. And they made numerical notes. They comment here that theorem 8 is mainly for theoretical calculations. Except for special cases, the algorithm in section 2.2, where you did you put the matrix A side by side with the identity, and did row operations on the matrix, say, to get it in, to get it row equivalent to the identity, and then the identity on the right side would be row equivalent to the inverse. That's the more popular formula. I mean, and it's a much better way to do it because, well, it's just more computationally efficient. Okay, so they make a comment here how Cramer's rules used in theoretical applications as well, but they comment that for larger matrices, Cramer's rule is hopelessly inefficient. Okay, so now you know about the Cramer's rule. Now you know about Cramer's rule. And there's a few other things too that we need to be familiar with in section 3.3. One is, well, are there any questions so far? Okay, Cameron's good. All right. So Theorem 9 here talks about a geometrical interpretation of determinants. Okay, so if you have, according to Theorem 9, if you have a 2x2 matrix, the area of a parallelogram determined by the columns of the matrix A is equal to I'm going to say this the right way, the absolute value of the determinant of A. And if a 3x3 matrix, the volume of a parallelepiped determined by the columns of A is the absolute value of the determinant of A. Okay, so I don't know if you have heard of this. Does anybody know of this concept relating the absolute value of the determinant of a matrix with the area of a parallelogram or the volume of a parallelepiped? Okay, first for Cameron. Mikhail says, all right, he thinks maybe in one of the homework questions there was something like that. It's possible. Yeah. So let's look at how this would be. Let's actually prove this. But one moment, I'm getting something out here. One moment. I want to have this in front of me. Yeah, we're going to prove Theorem 9. So let's go ahead here and go to the slides. Okay, we're going to prove Theorem 9 from section 3.3. And let's see, you know, it's sort of an amazing result. And we should try to, take a look at what they're doing here. So I kind of have my own proof of this, but it's based off of the Theorem 9 proof. Okay, so we want to prove Theorem 9. I'm going to prove the part where it says that the area of the parallelogram. Hold on. We can do better than that. Okay, so the area of the parallelogram equals the determinant of A. Okay, so let's go to the next page here. And you see I have two pictures here. And the first picture, okay, I have an area. Okay, I have an area. But it's a rectangle, right? But a rectangle is a parallelogram. It's a type of parallelogram. And the sides of the rectangle are determined by this vector here, which has components A and 0, and this vector here, which has components 0 and B. I mean, if you think about it, that's coordinate 0B, coordinate A, 0. Okay, so we know the area of this rectangle here would be base times height. So the area is A times B. Now, what if we were to look at the determinant of a 2 by 2 matrix whose columns were equal to the two vectors? Well, for that particular determinant, we would get the area of the rectangle, A times B, right? Because for 2 by 2, the area would be, the determinant would be A times B minus 0 times 0, and that equals A times B. So for this special parallelogram, which is a rectangle, indeed, the area of the parallelogram determined by the columns of the matrix A, okay, is equal to the determinant of A. But I'm not even worried about the matrix A. I'm just using this as an example. Okay. Notice I didn't call anything a matrix A yet. I'm just saying, hey, this is true above. Now what I want to do though is I want to go to a parallelogram, a more general parallelogram, the one you see down here below. This parallelogram has, what's determining that parallelogram? Well, the column, the point here, hold on, this is A0, so here's the vector A0 with those components, and up here that point there has coordinate AB. And so there's the vector AB. Now, it turns out that the area here, what would the area be? What would the area be? Well, so you have this base with distance A, and you have this height of B. So this triangle here has area 1/2 AB. Okay. And if I just sort of complete the parallelogram, let me just complete it. Like that, right? We have another triangle here that also has area 1/2 A times B. Okay. Now, I want to say this the right way. Would you agree that to find the area of the parallelogram, right? Because this also has length A, the area of the entire, if I wanted the area of this parallelogram, what would the area be? What would the area be of this big rectangle here? What would the area be for that big rectangle? It has base 2A. That's right, Cameron. So, and it has height B. So the area, almost right, would be 2A times B. But what we're going to do is we're going to subtract 2 times 1/2 A times B. That's this triangle here and this triangle here. And that gives us the area of the parallelogram. And that's going to equal A times B, because 2 times 1/2 A times B is AB. So geometrically speaking, that parallelogram, whose if you think about the now a matrix A, who has column vectors A0 and AB. Okay, well, the parallelogram here with those two column vectors in that matrix A, that parallelogram has area A times B. Okay, so that really, but okay, that's fine, but we need to show that the determinant of A, okay, equals A times B. So geometrically, we can see that yes, this parallelogram here whose columns are determined by the vectors A0 and AB, that parallelogram has area A times B. But the theorem 9 says, well, prove that the determinant of that matrix A equals A times B. And it's not hard to prove because you know properties of determinants. Okay, the determinant of this matrix A here would equal, which has columns A0, AB, would be the same as the determinant whose columns are A0 and 0B. Now, how am I getting that? I took negative A over B times the second row and added it to the first row and replaced the result in the first row. Does this particular row operation change the value of the determinant? It doesn't. So the determinant of that matrix A equals this determinant, and we already established that equals A times B. Okay, so geometrically you see, I mean, I guess probably we just could have gone here, right? We could have gone right to here. I mean, what I'm trying to say is, knowing this, hold on, let me blow that up here. Knowing this up here, okay, allows us then, through properties of determinants, the row operation that we did is a row operation that does not change the value of the determinant. It's actually, it's theorem 3, property A. So this proves the theorem. This proves theorem 9. And geometrically then, I mean, with this proves theorem 9, and geometrically, based on the picture, you can see that a matrix A whose columns are determined by vectors A0 and AB, that parallelogram would have to have area A times B. So geometrically you can see it, and now you can see it, how it works with the determinant. Are there any questions on that? Okay. Okay, so I'll just point one more theorem out here in the book. Okay, it has to do with theorem 10. Let me go there and find it. Whoops. Theorem 10. Okay, so determinants can be used to describe an important geometric property of linear transformations on a plane and an R cubed. If T is a linear transformation and S is a set in the domain of T, let T transformation of the set S be the set of images of points in S. We're interested in how the area or volume of the transformed object compares with the area or volume of the original set S. Okay, so they have a theorem, theorem 10, that tells you how you would find the area of a transformed region, and if you have a volume, the volume of a transformed region. It's basically the absolute value of the determinant of A. You need the absolute value because the determinant can be negative, right? So absolute value of the determinant of A times the area of S would be the area of the transform region S, and the absolute value of the determinant of A times the volume of S would be equal to the volume of the transform region. Now, I have not used this personally in my like in mathematical career, like in graduate school, you know, but I know for geometric type applications, it's pretty important, pretty important. So, for instance, let's go to example 5 here. Just want to show it here. I want to go right to the example. So in example 5, let A and B be positive numbers. Find the area of the region E bounded by the ellipse whose equation is given here. Okay, so I'm sure you've all seen the equation of ellipse in standard form. That's what you have, and then you have a picture on the left here, okay, that has the ellipse, okay, and they claim that E is the image of the unit disk under the linear transformation T determined by the matrix A. Okay, so if you, I want to say this the right way. Let's see here, one moment. Yeah, yeah. Let me just check one thing, class. Let me just check one thing on this. Hold on. Just give me a moment. Checking one thing on this. I mean, what they're saying is absolutely correct because, I mean, this part here is correct because if I go to the board here, the whiteboard, okay, so if X equals A times U, okay, and A in this case is the matrix with row A0 and 0B, and the vector U is U1 and U2. Okay, what you're going to get, you have a 2, well, you have a 2 by 2 times a 2 by 1, you're going to get AU1 and BU2 when you multiply those matrices. So this means X1 is A times U1, which means then that X1 over A would equal U1. And similarly, X2 would equal B times U2. So X2 over B equals U2. Okay. So if we go back to the, well, are there any questions on that? All right, good, good. All right, thank you, Cameron. And if you look like in example 5, they had for the equation of ellipse x1 over a squared, x1 squared over a squared plus x2 squared over b squared equals 1. That's the standard form of an equation of ellipse. But if you were to write that equation in terms of u and v, since u1 equals x1 over a and u2 equals x2 over b, you could write this equation here as u1 squared plus u2 squared equals 1. So in terms of the variables u1 and u2, the ellipse is equivalent to an ellipse with x1 and x2 axes is equivalent to a circle with the u1 and u2 axes. Okay, and that's what they are getting at. That's what they're getting at in the picture on the left. Okay, so under the transformation, you map a circle with axes u1 and u2 axes to an ellipse with x1 and x2 axes. And so the area of the ellipse, which is, that's not probably easy to get, right? We can get the area of a circle, but how do we get the area of an ellipse? We're using the formula. The area of the ellipse is equal to the area of the transformation of region D, and that would be the absolute value of the determinant of A times the area of D. Well, the determinant of A is just A times B, and the area of that circular region is pi r squared. So that's the circular region D is radius 1, so that's pi times 1 squared, and you get pi times AB. So you can see it has its uses, the theorem. It has its uses. It's actually tremendously powerful. I didn't want to cover this section without talking about that theorem and an application. Are there any questions? How many think Cramer's rule is pretty cool? Okay, Mikhail's liking it. Okay. Does Mikhail have any company? Or okay, I understand. All right, that's fine. All right, camera's trying to appreciate it. I'll take that. All right, excellent. Well, let me go ahead and stop the recording here. Very good.